And our facilitator is right here already. Dr. Raymond Jules Kala.
So, good afternoon, everyone.
Good afternoon.
Thanks again for the opportunity that was given to me to share the little bit of knowledge that I have about reinforcement learning. After the presentation of Prof. Adetiba on the basic knowledge, the foundation to understand what reinforcement learning has already been done. But before I start, I wanted to ask a simple question to the audience about what do they know about reinforcement learning? What is their point of view? How do they perceive it? And if they have already something, if they do have some basic knowledge.
So once you you try to train dog to use the toilets, a good reward will be given to that particular dog. So continuously, once anytime a dog defecates anywhere around the environment, you flog the dog, which is indicating a bad reward. And once it makes it of the toilet, a good reward, like maybe a bone biscuit, to be given to it. And it continues like that. That is how the concept of reinforcement learning works.
Yeah, that's a good, that's a very good introduction. So reinforcement learning is all about guiding someone or an animal, or it was used in psychology. It also applied to us human. You provide maybe reward, or you provide punishment in case the person you are training is producing a bad or a good result. And the goal at the end is to the person or the agent who is affected by the process to always seek the reward instead of seeking, and try as much as possible to avoid the punishment. Okay, so this is the basic thing about it. And what you should also remember is here, reinforcement learning is a little bit like not at the complete opposite of supervised learning or unsupervised learning, but it's another way of seeing the learning process. So it's very useful in the case you want to design a system that needs to learn something about an environment, and not when you have not yet collected the data required to create your intelligent system. Because you also notice when we were talking about unsupervised learning and supervised learning, there was that main issue that was the data collection process. And that data collection process also has it can have a negative impact or even a positive impact. Everything will depend on how the data are collected in the case of unsupervised and supervised. But in the case of reinforcement learning, we are not in the side of data collection, because we are using a different way of designing the agent, the intelligent agent. Okay, so the idea or the description you give is a very good description. So it clearly shows what reinforcement learning is, and is what we'll be trying to understand today. Okay, let us start. So we'll start with the introduction, with a summary. Today we'll be talking a little bit about what reinforcement learning is at the introduction. And then we'll move on and talk about exploration, Q-learning, policy gradient, and then talk about hierarchical reinforcement learning, model-based reinforcement learning, and multi-agent reinforcement learning. So as introduction, reinforcement learning is a paradigm in artificial intelligence that focus on training agents to make sequential decisions by interacting with the environment. So it's a little bit like you take someone, you put it somewhere, you haven't collected any data about the environment where the agent is. but you want the agent to solve a problem related to the environment. So based on this simple definition or this simple sentence, you can directly see that when we talk about reinforcement learning, there are some basic elements that need to be taken in consideration. We have the agent, we have the environment, we have the actions, and then we have the rewards. So these are the four elements. And usually people will say it refer to the area element. That means you have agent, reward, and agent, reward, actions, and environment. So these are the elements you need to focus your attention on, because everything about reinforcement learning is based on those four elements. And designing a reinforcement and learning algorithm or system will be based on the design of these elements. So reinforcement learning on trial and error with the agent receiving feedback in the form of reward or penalty based on his action. So every time the agent will perform an action inside the environment will either give him a reward to say, okay, you performed the right action towards solving a specific problem. So in this specific case, the environment describes the actual problem to solve, and then the environment is the one providing the reward or the penalty to the agent, in such a way that every time the agent will be performing an action, he will know if that action is the right action or that action is the wrong action. Because depending on the action it will be performing, it will be receiving either a reward or a penalty. But for the agent to actually know how to move around the environment, we'll be looking at the policies that the agent needs to follow in order to always be on the right side of the penalty. So basically always having a reward instead of a penalty. So reinforcement learning draws his inspiration from how human and animal learn by interacting with the world. So it's basically how we're doing things. So let's take, for instance, when we like looking for something to eat. So if we decide to take maybe a given plant and decide to eat it, if it doesn't give us a running stomach, and if it has a very good taste, we can say, okay, that is the reward. But if it has a bad taste or giving us running stomach, it's basically a penalty. That means we have to avoid that specific plant. So the component of a reinforcement learning, we have the agent. The agent is the one who makes the decisions and always take the actions. The environment, external system in which the agent operates. The actions is a choice available to the agent. And then the reward is usually a numerical signal indicating the desirability of the agent's actions. So based on this definition, can you please give me an example of or basically improve your previous example on the dog that he receive a beating if he's doing something bad, and match these element, match the element of your example to the agent, the environment, the action, and the reward. Can you please match it with the dog example? So on that example, who's the agent? What is the environment? And what is the actions? And what can be the reward? Hello?
Yes, sir. I'm with you, sir.
Okay.
The agent is the dog.
Yeah, okay. The
dog.
The agent.
I said, the agent is the dog.
Okay. So what can be the environment?
The environment is the toilet.
The toilet.
Everywhere. The toilet, the environment.
Okay.
Yes, that's you said that the environment is the problem that is
okay.
that that describes, yes, the actually the actual problem that describes that leads to the solution.
Okay.
So the toilet, the environment, the toilet, the environment is actually the environment.
Mm-hmm.
Then the action is the dog moving
Mm-hmm.
moving between the environment, the space where he is, and the toilet.
Okay.
Yes, and the reward is punishment that is beating or receiving a biscuit or a bone.
Okay.
For good reward, it will be biscuits. If for bad reward, it will be flogging of the dog.
Okay. So that's good. So with that example, you clearly understand that everything is around the agent moving inside a given environment. So the question I'm asking you, what makes this problem difficult?
Come again with your
I'm
question.
asking what makes the problem difficult? Where does the difficulty of this problem came from?
Okay. I feel it could be the dog knowing where to use.
Mm-hmm.
Yeah, I feel because the dog feels the environment is a safe space for him to use instead of the
Okay.
toilet. But we're training that dog to
Mm-hmm.
know that the best place for him to defecate is actually the toilet, not the
Exactly.
space where he
Mm-hmm.
moves or plays around.
Okay. So you understand that in this specific case, and I'm going to ask this question, if the environment doesn't give enough information about how to move inside the environment, and the dog doesn't have enough intelligence to understand the actual environment and knows what action to pursue, will it be easy to solve the problem?
So I didn't get that, sir.
So I'm asking this, okay, very simple.
Okay,
Well,
sir.
in this example, where does the intelligence lies on? Where do you find the intelligence?
In locating the toilet, I think that's intelligence.
Okay, so let me ask, yeah, locating the toilet is actually the problem that it needs to solve. But I'm asking, in order to solve it,
Okay.
where does it need a certain intelligence to do it?
Okay. In that means I don't know there's another maybe a corresponding agent also that we need to direct the dog, maybe using a trail to direct the dog to or maybe I don't know something. I'm not so sure of that.
Okay,
Yes, sir.
so I wanted to come to a certain conclusion, but I was hoping you will come to that conclusion is that the agent needs to embark a certain intelligence in order to be able to quickly understand his environment, because the environment will always be sending signals and it will tell him if what he's doing is good, it will tell him if what he's doing is bad, and also the environment will tell him how to move inside the environment and to get to the goal. But it will also tell him when he's moving on the right direction, on the wrong direction. So, but if the agent doesn't have enough intelligence to capture those information, the agent won't be able to produce the result he wants or he expects at the end, which is always receiving rewards. So the next slide is actually the objective of reinforcement learning is all about discovering an optimal policy. So the objective here is to find an optimal policy. So the policy here is, in fact, everything that the agent needs to do to achieve his goal by obtaining the maximum reward. So that is the policy. By a very simple definition of the policy is that. So the agent is making sure he's achieving the goal given to him by the environment, but doing it with the maximum reward possible. So that is the policy. So basically, it's a strategy guiding the agent to make action that leads to the highest cumulative reward. So the reinforcement learning framework is basically, it's associated to these 5 elements that is displayed on the screen. The first one is obviously the environment. The environment can be the world. We need the rewards. The rewards is just there to guide the agent, to tell him that whatever he's doing right now, it's producing results, it's guiding him in the right direction, and so on. And then you have the agent. And you need to understand why the agent here was represented using a, how do you call that structure on the screen for the agent? Can someone help me?
Can you ask the question again, please?
So I'm asking the agent, there's a small image under the agent element. What is it?
Network.
Yeah, it's a neural network. It's just to tell you that the part of the intelligence associated to reinforcement learning is on the agent side. So the agent needs to have the intelligence. The intelligence of the agent in this case is based on the design or the creation of the best policy to interact with the environment. So, and the agent needs to be trained. So after creating the neural network, you need to train the agent based on some observation he will be doing. And the training is also based on how he's interacting and what type of reward he's receiving and so on. And then you have the deployment. The deployment here, you have a robot. Just to tell you that in most cases, reinforcement learning are designed for robots. In real life, they are used by robots to solve problems that have been designed by that can be proposed in some area of research and so on. So what are the application of reinforcement learning? The first application is robotics and autonomous system. So can you give me an example of autonomous system that you know? And how does reinforcement learning apply to it? An example, please. Autonomous system.
Autonomous systems include self-driving cars.
Exactly. And how does reinforcement learning apply to self-driving cars?
Possibly if the car violates traffic rules,
Okay.
for example, when it sees a red light and still moves, a reward or a penalty in that case can be given, such that
Okay.
whenever that situation arises, the car would know that red means stop.
Okay. So with the case of autonomous driving, what is the environment in this case?
Environment is the road.
The road.
Yes,
Sure,
sir.
it's only the road.
Not the road, other vehicles, human beings,
Yeah.
the traffic lights,
Yes.
the surrounding environment.
Yes. The surrounding environment. The surrounding environment is basically the real the actual environment. So what can be the actions?
The actions from the autonomous vehicle could be to turn
Yeah.
right, turn left,
Yes.
to stop,
Yes.
and to speed, to increase the speed.
Yes.
Yes, I think those are the basic actions.
Yeah. They can also have hooting and indicating and so on. So that's good. That's very good. So another person, if possible, for the case for game playing, sorry. For game playing, anyone? Just give you an example of game and then we can look.
For game playing, I know there is an AlphaGo
Yes.
System that was implemented by DeepMind, I think, that was able to beat a master in
Chess.
the Go game.
Yes. Okay. That's good. So we have you have also many other examples like resources allocation. And then, do you think reinforcement learning can be applied to resources allocation?
Resource allocation, yes.
Yeah. How?
In cognitive radio, for instance,
Okay.
where cognitive radios that use dynamic spectrum allocation, where, for instance, the TV white spaces that have been opened for transmission for opportunistic use. So, for instance, if the security system in Covenant University wants to communicate using a frequency that has been assigned to a licensed user, however, that licensed user is not transmitting in this environment, and the security system want to opportunistically use that frequency since it's not since the frequency is not being used here. The radio system should be able to detect those frequencies that are unused and then dynamically allocate those frequencies for that radio, for the radio system to be able to communicate at that time. And then if, for example, if while it's in use, it should automatically also be able to detect if the primary user begins to transmit, it should be able to detect that, okay, this frequency is, there's a signal coming in this direction, and then dynamically change to some other frequency that is not being used at that particular time.
Okay, that's good. But in that case, how will you apply the rewards and the penalty in this case?
So when the interferences, for example, because if the primary user is transmitting or the licensed user is transmitting and the cognitive radio system is also transmitting, there will be interference. So whenever there's an interference upon choosing a frequency, then the reward or the penalty can be given in that case.
So it will definitely receive rewards if there's no interferences, and penalty in case there's interferences on the given radio signal. That's a good example.
Yes, sir.
Very good example. So let us move to the next one. So the achievement in terms of reinforcement learning is notable success of reinforcement learning include mastering complex games like the Go and the chess, as well as application in optimizing resources allocation, finance, and healthcare. So ongoing development research are exploring innovative algorithm strategies for real-world complexity and method to scale reinforcement learning to more challenging problems. So one of the recent applications is the integration of reinforcement learning to the LLMs, large language models, and some maybe not well-known application of reinforcement learning for object recognition or object detections can also be considered. So interdisciplinary nature, reinforcement learning sits at the intersection of computer science, neuroscience, control theory, offering promise for developing intelligent systems capable of autonomous decision making in dynamic decision making in a dynamic and uncertain environment. So some people even consider reinforcement learning like the introduction to a much more evolved intelligent system compared to the supervised and unsupervised because of the adaptability characteristics of the reinforcement learning models. So what are the benefits of reinforcement learning? So reinforcement learning is applicable to a wide range of complex problems that cannot be tackled with machine learning algorithm. So reinforcement learning is closer to artificial general intelligence, as it possesses the ability to seek a long-term goal while exploring various possibilities autonomously. Here, it simply tells you something. If your environment is clearly defined and you design a reinforcement learning algorithm, that reinforcement learning algorithm, if set up properly, will be able to find a solution. because it simply focuses on the problem as a whole. It does not need a separate data collection step, which is one of the limitations of the supervised learning approach, because on the supervised learning approach, the data collection step is a crucial step. And after even collecting the data, there's another step which is called the feature engineering step, which is very important. It's even much more important in some cases than the classification phase, because if you miss that phase, you can completely destroy your system at the end. So reinforcement learning, it works in dynamic and uncertain environment, which clearly describe the world in which we are. It's a dynamic world. Anything can happen at any time. And I think that is the reason why it was used a lot, and it's still being used when it comes to the design of autonomous driving system, simply because the road is a dynamic environment. It's uncertain. It's an uncertain environment because you will not be able to control what the driver next to you is doing. You will not be able to control whatever is happening in front of you, because anything can happen on the road. And that is the reason why reinforcement learning is the good approach to perform or to design system like autonomous driving system. So what are the challenges with reinforcement learning? While reinforcement learning algorithms have been successful in solving complex problems in diverse simulated environment, their adoption in real world has been slow. First of all, the reinforcement learning agent needs extensive experience. That means needs to go through the environment as much as possible and collect as much information that he needs about the environment to be able to maximize his reward. We also have a delay reward. That means in some cases, the system might not be providing the reward as it's basically the environment that provides the reward. And providing the reward is also based on the process of evaluating the agent and so on. And in some cases, the reward might arrive when the agent has already moved into the next step and so on. And he will not be able to collect the reward and know that the previous action he performed is actually the best course of action. And also, one of the main issues is the lack of interpretability. Can somebody tell me what it means, the lack of interpretability? Because if you have been working with AI this past couple of months or years, you should understand what's the meaning of interpretability in terms of AI. Can somebody answer? What is the lack of interpretability? Anyone?
So interpretability would mean if there are changes in the parameters within the system, or if there are changes within the system, how to interpret what exactly will be the effects of those changes in the final output, or what will be the effect, what consequence, as it were, would that change in the parameters within the system bring?
Okay, that's good. It's all about understanding how the system works and what result does it produce based on certain parameters. It's one of the main issues with AI at this moment, because people need to understand how the machine takes decision. And sometimes even the parameters are not enough to produce a good interpretability, because some parameters, there might be some slight changes somewhere, and then even if the parameter looks alike, the machine will be taking a different conclusion at the end. So with reinforcement learning, the interpretability also is one of the main issues, because the agent might take one direction without giving any clear explanation why that specific direction was chosen compared to the other directions. So that's the issue. And in AI and ethics, which is the new field that is being created right now, the notion of interpretability is really important. So basically, to support the adoption of AI in autonomous driving specifically in field like medical, in health systems and so on. So the ethics expert, they want the interpretability. That means based on any situation, they need to be able to understand, or the machine to tell them why that specific decision was taken compared to any other decisions. So reinforcement learning versus supervised learning and unsupervised learning. So you have been working, or you had a very good introduction in terms of what is supervised learning and unsupervised learning, but it's also good to see or to understand what is the difference between these three well-known approaches, learning approaches. So supervised learning is a paradigm of machine learning that requires a knowledgeable supervisor to create a labeled data and feed it to the learning algorithm. So here you have a supervisor for the supervised learning. He's preparing the data, he's making sure everything is clean enough for the system to clearly understand or to clearly produce a model to understand the data. So with reinforcement learning is a separate paradigm of machine learning. Reinforcement learning does not require a supervisor or a pre-labeled data. It doesn't need that. Instead, it acquired training data in the form of experience by interacting with the environment and observing its response. So in this specific case, for the reinforcement learning, the agent will be interacting with the environment and he will be receiving feedback from the environment. Based on that feedback, he will always try as much as possible to obtain the positive feedback instead of receiving the negative one. So on the unsupervised learning is a technique that determine patterns and associate in that determine pattern and associate in unlabeled data. So for the unsupervised learning and supervised learning, we always have data as input, but for the reinforcement learning, there's no data, but the agent is basically learning from interacting with the environment. So these are the main differences between reinforcement learning, supervised learning, and unsupervised learning. Now, do you have any question for me before we start getting into the part that interests us today, which is the first one? We will be talking about the exploration, the Q-learning policy, and the policy gradient, which is the first element in our list of topic to talk about today.
Yes, I do have a question.
Yes.
Yes, I want to ask a question in the problem space of cloud service negotiation. So basically, the problem space involves trying to create a framework, a model that can probably enable agents efficiently negotiate terms between the service provider and the service user. So I'm seeing how the possibilities of applying reinforcement learning in this space. See it can handle complex range of problems.
Yes.
But one area I would want to know is, one of the drawbacks is delayed rewards and lack of interpretability. Are these challenges negligible in that field? For the rewards or the benefits of reinforcement learning in this space, and we have this kind of challenges, are these rewards kind of negligible in terms of the kind of things we can explore with this reinforcement learning? Yeah, that's my question.
Okay. So I'm going to try to provide an answer to the question. So your issue is about cloud service negotiations.
Yes, sir.
And the first question, I'm going to say, is it similar to resource allocation? I think it's similar to resource allocation.
It's similar, but in the particular one where basically you have agents representing a cloud user, a particular agent representing a cloud user, and another agent representing a cloud provider. They're trying to negotiate favorable conditions
Yeah, they have to negotiate a favorable condition, but the
Yes.
question I'm asking is simple. If it's doing cloud service negotiation, so basically one is trying to have access to the cloud service. The first
Yes.
thing you need to identify is which part in this specific problem represent the environment. Is it the set of cloud service that represent the environment, or there's a broker making cloud service available to all the agent that needs access to those cloud services?
There's a broker.
Yeah, you have a broker. So when you come to cloud service provider, so you have a broker. So the broker is basically the one who's going to tell you if the services you want to access, is it still available? Is it not available? And it's also going to tell you if there's anyone who also want that specific service. And it's all about the politics that you will be implementing, or the policy that needs to be implemented in order to guarantee that each agent asking or requesting an access to a cloud service will always be served the optimal way. So in this case, you need to clearly define the environment. You basically have the broker. The broker will be the one basically answering all those questions about any request sent by the agent. He will tell him is available, and he'll maybe in some cases might tell the agent requesting for the cloud service that there's another agent maybe using that specific cloud services, or maybe he needs to define his own priority in order to have access to it. So in this specific case, when you talked about interpretability and the ethics side of it, it all depends on the problem or the service that you are making available. So for instance, if the cloud service doesn't imply or doesn't have a direct impact on real life situation, like what, let's say that cloud service doesn't make medical services available to people online, or does it impact someone's life and so on? If it's the answer of all those questions is yes, you might need to think about interpretability on the ways the resources is being allocated, because a wrong answer or a wrong allocation might have a direct impact on someone's life at the end. And in that case, you need to take a very good care of the interpretability part, because at the end, they will need to go back if there's a consequence later on to see what was the reason why a given decision or a given allocation was done. I don't know if I answer your question.
Yes, you did. And I think that also answers the question for delayed rewards if it's also negative. So it depends on the particular
depends on the particular problem you have at hand.
Yeah, thank you very much.
So any other question? Yes.
Question. Okay,
Yes.
my question goes like this. In reinforcement learning, you said that it doesn't require data, although we have been told from the beginning of the section that AI works on data, that based on the data that is being provided, it actually works on it and then gives out our desired results. Just like in the case of where the IRIS data sets, we can actually work on that data set, and based on those features that are there, we can actually determine which type of plant, assuming you go out the carrier algorithm, design, then which type of plants this particular IRIS data set would be based on the data set that has been provided. So what got me thinking is that if there's no data provided for reinforcement learning, and it works based on learning from experience, the results that reinforcement learning give, is it based on the reward, or is it that as it's being put in a particular scenario, a problem, it learns, acquires knowledge and stores it somewhere? Something that has been, got me thinking for a while. So I just want to be clear on that. Thank you, sir.
No problem. No problem. So that's a very good question, but I think the answer is coming on the next slide, but I'm going to give it to you directly. So the first thing you need to remember is an environment always come with all the problem the agent needs to solve. And that is how it's basically the policy and the reason why there's a policy that is designed. So the environment already carries the problem, and the environment is the one in charge of providing rewards or punishment. Because if you like moving away from the actual objective designed by the environment, you will be receiving a punishment. But if you are getting closer and closer, you will be receiving rewards. Do you understand? Is it okay?
Yes, sir, it's okay.
Okay.
Mr. Thank you so far, sir. This promise speaking.
Okay.
So my question is quite close to what she asked earlier, but quite different. You made mention earlier that there's a level of intelligence required by the agents, which is one of the
Yes.
problem in reinforcement learning.
Mhm.
So I want to know, how will that level of intelligence be acquired in the first place, since there's no training? So I was thinking that maybe it could be a form of supervised training to acquire that first level of intelligence. Then, sir, please, could you just help go up to the previous slide? I saw something that was not very clear. Yes. So, sir, I think it was saying that it requires that reinforcement learning requires training data in form of
Acquired.
experience by interacting with the environment and
Yes.
observing. Okay, it acquires training data in form of experience. So, sir, the data is acquiring, is it not used for training? Because we said earlier that there's no training.
No. I didn't say there's no training. I said there's no data.
Okay, it's
Training
not based
data.
on
There's no
data
training data that are previously prepared, but there's training. And it's
Okay.
basically what we will be doing today after all this literature part. We'll be looking at how to basically implement a very simple reinforcement learning agent inside a given environment. So the agent is trained, but if you remember, I showed you the reinforcement learning framework, this one, and you notice that under the agent you have a neural network. You can't have a neural network if you are not going to be trained. Okay, so a neural network is a direct thing to say there will be a training, but that training will be based on the data collect from the environment during the observation and the experience that the agent will be collecting from the environment. Is it okay?
Yes, sir, it's okay.
Okay. So can we move on?
Yes, sir.
Okay. So exploration, Q learning, and policy gradient. So the exploration part, it's more like you have someone who doesn't have a memory. So all he knows is he needs to move around until he will get to his goal. So the exploration part means there's no strategy during the agent movement inside the environment is not based on any strategy. It's just moving around, not following a clear path. He's just trying as much as possible, trying all direction, and try as much as possible to achieve the goal that is defined by the environment, but not following maybe a certain policy that says maybe you have to move left, go up, go down, and so on. And he's like moving randomly around until he'll see if he's achieving the goal that was done or that was defined by the environment, or he's not achieving it at the end. But that is the part related to the exploration. For the Q learning, we'll be looking at something called the Q table. So now there's a certain strategy behind. So every time the agent is performing, every time the agent is performing an action, he's saving it somewhere in a Q table. And every time he's maybe receiving a reward because he moved a certain way, he's also saving it inside the table and use that table as his knowledge base for later on. For the policy gradient now is based on the gradient analysis that you saw earlier, when you were doing supervised learning. So it's basically, it's close to that approach. So let us look at the exploration. So in the exploration, in reinforcement learning is a crucial aspect that deals with how an agent should explore the environment to discover optimal or near optimal policy. So the epsilon greedy, the agent, you have the exploration based on the epsilon greedy. In this case, the agent select the action with the highest estimated value with a probability of 1 minus epsilon. For the softmax exploration, the probability of selecting an action is determined by the softmax function applied to the estimated action value. For upper confidence bound, the agents select action based on their upper confidence bound, taking into account both the estimate value and the uncertainty in the estimate. So you also have the exploration based on Thompson sampling. The agent maintains the distribution over possible model of the environment. So you have the bootstrap deep Q learning. In deep reinforcement learning, multiple value estimate Q network are maintained. So you have the count-based exploration. The agent maintains count of how often each state or state action pairs has been visited. You have the intrinsic motivation. The agent is equipped with intrinsic reward signal that encourage it to explore novel or uncertain state. So you have sparse reward shaping. It's modifying the rewards structure to provide separate rewards for accomplishing high-level goals. Can encourage exploration also. You have parameter noise, injecting noise into the parameter of the policy or value function during training can encourage the agent to explore different regions of the action space. So you have model-based methods. Okay. So for the exploration base, I think the first two are related to the exploration phase. The rest, I think they are, I kind of mixed up a little bit because some of them are related to the Q learning and the model-based method. So just consider the epsilon greedy and the softmax exploration, and also there's the random exploration that you should consider. The rest are a little bit general. It also includes the Q learning and the policy gradient. So for the Q learning, the first objective for the Q learning is the aim is to learn the optimal action value, which is QS, the couple QS, which is the state and action, which represent the expected cumulative reward of taking action A in a state S and following the optimal policy thereafter. So the update rules. So in this case, the update rules follows the Bellman equation. So the Q learning update rules is based on the Bellman optimal equation, which says you state the state at A and S, it's equivalent. We'll take the state at that specific position times alpha, which is the learning rate, times R, the rewards, plus gamma, the discount factor, with the maximum of the previous, the input at the previous state and the next actions minus the actual state, minus the input of the Q learning table corresponding to the actual action we have and the current state. So for the exploration part on the Q learning typically use an epsilon greedy strategy for exploration with probability epsilon. The agent chooses a random actions and with probability of 1 minus epsilon is choose. The action with the maximum Q value is also selected. In the case of off-policy, Q learning is an off-policy algorithm, meaning it updates the Q value based on the maximum value the maximum Q value of the next state, regardless of the action taken. So this is another description of the Bellman equation. So Q new is the new state. It's equal to Q of the old value inside the Q table corresponding to the state T and the action T. Alpha is the learning rate. RT is correspond to the reward as we saw. And then gamma is the discount factor. And then you can look at the maximum value or the estimate optimal feature value of inside the Q table minus the old value of the Q input inside the Q table at the state S and the action AT. So till now, any questions?
Yes, there's a question.
Yeah, okay.
My question is, how do you know which exploration technique to use?
That's a good question. It usually depends on the problem. There are some problems that an epsilon greedy exploration approach can be used, but most likely it depends. If the problem is a very simple problem, in most cases, the epsilon greedy can be used. Like it also, when I said simple problem, it depends on the type of information sent to you by the environment. So if the environment is a complex environment that sent a lot of information, the epsilon greedy won't be enough to solve the problem. But choosing the right exploration approach, it's also a difficult task because in most cases it's by trial and error that you choose the right policy, or not the right policy, the right exploration approach. So you can try one. If it doesn't work, you can try another one. But in most cases, it's better to, depending on the number of information sent to you and the complexity of the environment, it's what helps you, it's what guides you on what policy to choose, and not what exploration approach to choose. You can choose the much more elaborated one if the problem, if the environment is a complex environment, you can choose a much more elaborated one. But if the environment doesn't provide a very difficult, it's not really complex, you can choose a very simple exploration approach like the epsilon greedy approach.
Thank you, sir.
Any other questions?
So, is there any difference between the Q learning and the epsilon greedy exploration?
Q, yeah, there's a difference because look at what is inside the Q learning. Q learning is like a methodology. It's a way of the agent is achieving his goal. So it needs to, the exploration is part of the Q learning approach. So if you look at the Q learning, you have an exploration section. And in that exploration, it says the Q learning usually it follows the 1 minus epsilon, which is the epsilon, which is epsilon greedy explorations.
Okay, so because some articles, most time when I make a reference to using learning, they also bring in the aspect of epsilon greedy. So I'm always confused whether the two of them are the same because
no.
I use it interchangeably. Okay, so thank you.
So breaking down the Q learning process, so it's basically an algorithm. So the first thing, the Q table needs to be initialized when you are doing the Q learning process. So the Q table looks like this table. It's like you have the corresponding action and then you have the states. And then initially everything is at 0. And the system, based on the interaction with the environment, those values will be slowly replaced by the elements by values different than 0. And that will guide the agent. Every time he's at a given state, he will know what state he needs to follow in order to achieve his goal at the end. So the agent will start exploring the action. So for each state, select any one amongst all possible action for the current state, and then travel to the next state, which is S prime, as a result of that action A. For all possible action from the state S prime, select the one with the highest Q value. Okay, so every time he will be updating it, and then if it's coming back to a given state, he will simply choose the one with the highest value to move on to the next one, and then proceed by updating the Q values using the equation that was given, which is the Bellman equation, and then set the next state as the current state, and then repeat the process. If the goal state is reached, then end and repeat the process if not. So it's basically how the system is actually updating the Q table using the previous equation that you just saw. So our first exercise is this one. So consider a simple 3x3 grid world. An agent starts at the top left corner and has to reach the goal of at the bottom right corner. The agent can take up, down, left, and right. Each action moves the agent one step in the corresponding direction. The environment has a reward of 1 for each step, and reaching the goal state as a reward of 10 plus 10. So the first thing I want to see is the initialization of a Q table for the environment, and apply the Q learning to find the optimal policy. So I just want you to give me the structure of the Q learning table and tell me how Q learning will find the optimal policy. It's all I want. Just tell me how you will do it and give me the structure of the Q learning table, of the Q table. Do you have the answer? Yes. Mr. Julius?
Yeah, so I'm thinking that for the Q table,
Yes.
so the rows must be the number of states.
Yes.
Here we have it as 3x3 grid, so that would be 9.
Okay.
Then the columns would be probably the actions that you can take. So here we have 4 actions, like 4 actions that you can take up, down, left, right. So the columns can be 4, and the rows can be 9 for the Q table. How that's right.
Okay, so the Q table, what will it be? It's basically the nature of the Q table that I'm interested in.
The Q table will be like how do I put it? A matrix. Let me just put it like maybe a matrix with values for each of the actions.
With values for each of the actions. So initially, what is it?
Yeah, up, down, left, and right.
No. Initially, what are the values inside the Q table?
Maybe 0.
Yeah, it's zeros. It's a matrix of zeros. And can you please give me the equation to update these values?
We can use the Bellman equation you use.
Yes, we can use the Bellman equation. Okay, we can use the Bellman equation. I think everyone can see it easily. So that's true. So the input matrix, or the matrix, the initial matrix of the Q table will be a matrix of 0, a 3x3 matrix of zeros, and all the values inside will be updated using the Bellman equation with the parameters gamma equal to 0.9 and alpha equal to 0.1.
Yeah.
Yeah, that's it. So next exercise. Can someone answer, please?
Okay, yeah. So for the first one, a recommender system. You can model it as an unsupervised learning.
Okay.
An association.
How?
So we have the data for all the customers, and then we try to group probably cluster the customers into some points. And then for every friend in that cluster, we recommend potential friends within that same cluster to that person.
Okay.
Or we can use graph neural network to look at your graph. If you're related to someone and that person too also has a connection that you might be interested in.
Okay.
Then for B, I'll take it as supervised because we have the topics already. If you have the topics already, probably to maybe categories. So you might want to categorize for every news, you want to categorize them into their categories. So if you have them, then that'll be supervised learning.
Okay. Doc, I think Julius should also allow others to
answer, yeah.
to answer.
Next person.
It will be like others are not carried along.
Yes.
Who wants to have a go at, if you have a divergent view from what Julius gave, or you want to attempt B, C, E.
Yeah.
Longer, the spoken.
Yeah, that's that view already.
No, I said
No, there's CDE now. CDE.
Yeah, that's how Julius and that's how A and B.
Yeah. Oh, okay. Yeah.
I want to attempt for E. So, for my thinking, E is going to be a supervised learning to capture those front-end transactions. So, it should have been labeled earlier before during the training process.
Okay.
I think C should be reinforcement learning because it's actually learned from or supervised.
Okay, for D, I'll go for supervised learning. In that case, whenever, let me say for instance, when you purchase something on Jumia, probably maybe shoes, you go to the shoe section and you purchase a particular shoe. Probably when you're making use of your system, maybe you Google on Facebook, it will show you different types of shoes that, okay, this shoe is available. You can actually purchase this particular price for it. So D will actually be a supervised learning because it gets images relating to shoes or any particular item you have visited the particular store on Jumia.
All right. Okay, let her counter. There's a counter argument. There's a divergent view here.
Okay, that D can actually be unsupervised. Like it can be a clustering. You can look at, okay, what has this person been buying? What kind of shoes does this person used to buy? Then you cluster them together. Like that's how it can be unsupervised also.
All right. I think we've gone through all.
E is still pending. The system in the credit card company
someone
captures
said something about that it's supervised.
I think there's an how to the question also. Maybe they should explain the person that said.
Yeah, I think they were giving explanations actually. So give your explanation.
Okay. So I said it's going to be supervised.
So why?
I'm trying to reason the answer again. If it's going to be supervised, because how will it know a front lens? Okay, so basically it should be a way of labeling some, maybe the transaction is extremely outrageous, and this person have been having a particular range of transaction. All of a sudden, there's an outrageous transaction. So it will be able to know that this transaction is not usual. So it can cut in between the two anyway. Because if we also say, let there be clustering can dictate if this particular transaction is outside the normal one, if it's abnormal also. It can also be, it can cut in between it. You can even be semi-supervised.
All right. Okay. Can we go on now?
So
I think Julius is also raising his hand. Maybe he has a question or he wants to respond.
There's a question.
Julius.
Yes, I want to comment on that, that it can be supervised and also unsupervised, depending on the kind of data we have. So if you have a data where each transaction is labeled as either fraudulent or legitimate, then you can treat it as supervised learning. But if you don't have a data set that has attributes, separate it as either fraudulent or legitimate, my model it as anomaly detection. So it's such that we're able to find unusual patterns in data that could probably indicate fraud. So it can be modeled as both supervised learning and unsupervised learning, depending on the data we have.
The goal of the exercise was basically to show you that in some cases, knowing if we are going to be using supervised or unsupervised learning is usually a very tedious task, and somehow the best way maybe to run away from there is to see if it's possible to let the system tell us what we are doing. So in some cases, it's better to use reinforcement learning approaches, especially when there's a confusion between a supervised learning or unsupervised learning. In most cases, the reinforcement learning is the good answer to that question. So especially for the credit card company that capture fraudulent transactions, that one I think is a very difficult problem because every day there's a new way of performing fraud with the credit card transaction. It's not only about stealing the details. It can be someone just taking picture of the information of your credit card, and it's a dynamic problem. So let's move on to the policy gradient. So the policy gradients are a class of algorithm used in reinforcement learning to learn the policy directly, which is the strategy that the agent used to select action in different states of the environment instead of estimating the value function as in value-based method like Q-learning. Policy gradient method optimize the policy by directly adjusting the parameter. So the following elements are the component of the policy gradient in the reinforcement learning. You have policy representations, which is the first step. So then there's a need to describe the actual policy that we'll be using. Use the objective function that will be, in this case, used to adjust the policy. And then you have the policy gradient theorem that will be used to play around with the policy using the gradient descent approach. And then you have the reinforce algorithm that needs to be selected. And then you have the actor critics method. And then you have the policy parameterizations. And then you have the entropy regularization. And then you also have the Bash policy gradient method, trust gradient policy optimization, and approximation policy optimizations. So these are the elements that describe the policy gradient. So how do I evaluate a reinforcement learning algorithm? So how can we evaluate a reinforcement learning algorithm? After looking at all the elements we discussed about earlier, how do you think we can evaluate a reinforcement algorithm? How can we evaluate it? Is there anyone to answer?
Okay, someone, all right.
Thank you, sir, for the presentation. I think one of the ways how we can evaluate a reinforcement learning algorithm is probably the agent there is able to give an optimized or an intelligent response based on the feedback it's been getting on and on while training. I think that's the way we can do that. Okay, the parameter, probably we can use something like accuracy or the error rates or we can use the latency, or what kind of delay do we have during the training? Thank you, sir.
That's a good answer.
All right, someone
Any
else
proposition?
wants to
Any?
respond?
Yes.
Sir, thank you, sir, for the presentation. So
Mhm.
another way that we can maybe measure is maybe the cumulative reward, maybe like the summation of the reward of which the agent has achieved over time.
Yes, that's good. It's the best way, in fact, to evaluate it. Any proposition? There's Julius with his hand, please. Mr.
Yes,
Julius.
yes, sir. Aside from using the cumulative reward, we also look at the convergence of the policy. So we look at if policy converges, that is, it stop changes significantly. So if you stop changing, then we know that probably the policy has converged to some extent.
Yes. But in this particular case,
Julius,
the policy.
so we didn't get
Yes.
you. We didn't hear what you said.
In your answer, I think you should add that the policy achieves the goal and it doesn't change. That will make sense, because if you said the policy doesn't change and you stop there, it simply means maybe the agent wasn't able to solve the problem and he's out of possibilities to achieve the solution. So it's better to say that he's designed a policy to solve the problem, he has solved it, and the policy is not changing, so he has achieved the optimal policy at the end.
Yeah, thank you, sir.
Okay.
Another one would
Any?
be
Yes.
the agent's behavior. That's based on the task given to analyzing the agent's behavior, the policy that's been given to him, if he's happy, if he's sad. That could be another way of evaluating the reinforcement learning.
Okay, that's good. So can anyone answer the next question, please?
Okay, sorry, sir, there's a question.
Okay, I'm listening for the question.
Oh, sorry, sir. Thank you, sir. So please, I have a question as touching the Hellman's formula for updating the Q learning that you gave to us the other time. Please, I want to ask that how do you come about the discount factor? That's the first question I want to ask. Then the second question is, I noticed in that formula that to update that you always, within that discount factor, at the discount function, let me call it discount function, you always subtract the old Q value within that discount function. Why do we have, or why does, or I don't know, maybe there is an explanation why the inventor had to subtract that old value from it before now adding it to the old value. Then my third question is, what is the meaning of that Q itself? What does that Q stand for? Thank you, sir.
From the end, the Q is an entrance. It's like one of the cells inside the Q table. That is the Q. The value. The Q is the value inside the Q table. It's what it stands for. Is it okay?
Okay, sir.
The next question, it's about, yes.
So my second question is, when we look at that temporal difference that is carved out,
Yes.
we have we have the learning rates, then we have the discount factor. But now the old factor, like the function says the Q equals to the Q old plus all the one we have there. Then I noticed that the Q old is subtracted from the one inside the temporal. So why do we have to subtract again before we now add it? Since we are using it to update, is it a system
To update?
Are there other algorithms that we can use to achieve something of this nature?
Yes, there's a different algorithm. This one is the Bellman approach to solve the problem, or the Bellman approach behind the Q-learning. But you can also use the SAS algorithm, which is similar to this one, with the difference that instead of using the maximum value, it simply use the previous value that was obtained and subtracting it to the actual value in order to calculate the new value by adding it to the next simply take the same Bellman equation and removing the max there, the maximum values. And the only risk with this is that you might have a negative value associated to that. It's possible to, it's kind of clear to have a negative value. And usually this formula, having a subtraction, it's simply to make sure that the value associated to the pure learning doesn't go further from a certain threshold that is usually defined. Is it okay?
Okay,
To
sir.
guarantee that the value will remain within a certain threshold, to avoid it going further out of that defined threshold. So you were asking a question. I think the equation, this one, you can also use a different equation, which is the SARS equation. Is SARS. Is it SARSA equation? Yeah. And that equation is similar to this equation, but in which you have removed the max value inside. Is it okay?
Yes, sir. It's okay.
Any other questions?
No, sir.
Okay. So the next question now is it possible to have overfitting with reinforcement learning? Because you notice when you were doing supervised learning, unsupervised learning, supervised learning especially, we have the case of overfitting. So is it possible to have it with reinforcement learning?
Yes, sir. It is possible to have overfitting in a
And how does
situation
it?
where
Yeah.
agents actually learn an environment to a point that it's now actually falling short, in a new environment or an unseen environment.
That's good. That is the reason why, even if you are doing reinforcement learning and the agent is learning from the environment, it's good to avoid achieving maybe a policy that is too, is kind of very close to the environment itself. So it's better to have a policy that is able to generalize at the end. So next, let's talk about hierarchical reinforcement learning. So with the hierarchical reinforcement learning, the reality is a little bit different. So the goal here is to learn, there is hierarchical reinforcement learning. It decomposes long horizon decision-making process into simpler subtasks. Have you heard of the term divide to conquer?
Yes, sir.
So
can you explain it to me?
So divide to conquer is when you have a big, large, complex problem, and then the problem is subdivided into different parts and solved independently. So an algorithm can be applied to each solved problem for a solution.
Mm-hmm. Okay.
So dividing a big task into subtasks and solving each subtask independently.
And then combine it to have the solution of to have the complete solution of the big task.
Yes, sir.
So it's basically the same thing when it comes to hierarchical reinforcement learning. So the goal here is to divide whatever the agent has to solve as a problem. And it's useful when you have a very big environment in which the agent needs to move. So you have some set of sub-environment in which the agent will design an optimal policy to move from one environment to another one, and then basically find his way around the big environment. So let's look at the example. Suppose the agent has a clear set, has to clear a set of dining tables. This includes the task of reaching and grasping the dish. These are high-level tasks on a lower level. It requires that task of controlling and moving the limbs and then fingers to reach out and grab objects and subsequently put them into a proper place. So the hierarchical reinforcement learning is designed with the same logic. So you have to decompose the task of cleaning the dish by understanding the fact that the agent has hands, and those hands, it's composed with fingers and so on. And then you have to move his finger optimally in order to solve the complete task, which is cleaning the dish. So there are multiple levels of policy, which you can identify one of the policy, which is how to efficiently move the fingers, how do you place the fingers to take the dishes and make sure you avoid breaking those dishes. So hierarchical reinforcement learning gives us multiple benefits during the training and exploration. So during the training, since high level correspond to multiple environmental steps, episodes are relatively shorter, thus propagating rewards faster and then improving the learning process at the same time. So on the exploration part, since exploration happen in a higher level, it is able to learn more meaningful policy and thus take more meaningful actions than those taken on the atomic levels. Example, an agent will learn better policy to reach the goal at the level of grasping object than at the level of understanding, joining movement or fingers. So it's more like you have maybe a complex task to perform. So you break the complex tasks into smaller, simpler tasks, and then you design a policy to optimize that process at each task. So if you have to, maybe in the case of the example, to move your limbs in order to take, you have a policy to optimally move your limbs in such a way that the next step, everything in the small task will be optimal. And if you add many optimal processes, you have the optimal solution to solve the problem. So hierarchical reinforcement learning provides a structure and modular approach to handling complex tasks, offering scalability and efficiency in certain scenarios. Effective hierarchy design and addressing challenges like suboptimal remain active area of research. Just to say that hierarchical reinforcement learning, as I was reading, it's still an open field of research in terms of reinforcement learning, because it's all about how do we clearly divide a problem into subtasks. It remains an open issue. So my question now is to you is, what is scalability?
Scalability is the ability for a system to actually work under an increased or expand situation or like that, sir.
Okay, that is scalability when it came to the cloud environment, which is also a good answer. So it's almost the same. Any proposition? Any other proposition, please?
No, sir, we are fine.
Okay. So hierarchical levels. So in the hierarchical reinforcement learning, you have to define the hierarchical level. The hierarchical level, you have the high level policy. It's responsible for selecting amongst different subtasks or options. So you have lower level policy. It is execute the chosen subtasks and provide detailed action at a lower temporal scale. And then you have options. Each options encapsulates a series of primitive action, creating a reusable semi-autonomous subtask. You have intra-option policy. So the intra-option policy provides detailed action during the execution of the option. You have termination condition. It's options have termination condition indicating when the options should end and control should return to the high level policy. You have learning at multiple level. So high level policy, learn to select option based on the current state and overall task. Lower level policy, learn to execute selected option, focusing on detailed subtasks. You have intrinsic and extrinsic rewards. Intrinsic reward associated with successful subtask completion or progress within option. You have extrinsic rewards, external rewards received from environment based on overall task performance. You have learning objective, high level policy learning aim to make effective choice of options. Lower level policy learning focus on executing option optimally to achieve subtasks. You have feasibility and suboptimality. Hierarchical reinforcement learning offers a more feasible exploration strategy in high dimensional states. Trade-off exists between suboptimality introduced by hierarchy and potentially efficiency gain. And then you have the element linked to transfer learning. So hierarchical learning facilitates transfer learning, allowing knowledge from solving one task to expedite learning in related tasks. Applications successfully apply in robotics, natural language processing, and game playing, where tasks involve hierarchy of subtasks. And then you have the challenges linked to reinforcement learning. Designing effective hierarchy is challenging. Incorrect design may lead to suboptimal solution. Learning to switch between options at the right time is a non-trivial problem. Algorithm. Various algorithms address hierarchical learning, including optical framework, Max-Q, feudal network, and deep reinforcement learning techniques for both high-level and low-level policies. So you also have the model-based reinforcement learning, which is the objective with the model-based reinforcement learning. It focuses on learning explicit model of the environment, capturing dynamic and state transformation. And then you have the component of a model-based reinforcement learning. It involves learning a transition model, how the environment evolves over time, and or rewards model. And then you have the planning linked to the model-based reinforcement learning. After learning, the model planning algorithm can be used to simulate and optimize future actions. And then you have sample efficiency. It can be more sample efficient compared to model-free methods in situations where real-world interaction are costly. The advantage of model-based reinforcement learning is effective in situations where the environment is well understood and modeling is feasible. It's suitable for scenarios where real-world interaction are expensive or limited. The challenges linked to it. The accuracy of the learning model is critical for successful planning. Planning using a model can be computationally expensive, especially in large state space. So we will just look at the model-based reinforcement learning, I think is we still have the last one is normally the multi-agent reinforcement learning. So all you need to remember about the model-based reinforcement learning is the advantages compared to the one we previously talked about. The model-based reinforcement learning is the situation in which a model of the environment is already made available for the system to go through it and then provide the optimal situation, the optimal policy for the agent to achieve his final goal. So the model-based reinforcement, what is model-based reinforcement learning? Is basically what we talked about earlier. And what is the model? The model is the representation of the environment in which the agent will be evolving. And how is the model used? The model is used to design the policy before actually applying it in real life. So for the multi-agent reinforcement learning, the first thing you need to remember is, in some cases, what we talked about earlier was only about having a single agent interacting alone inside a given environment. But what is going to happen if you have more than one agent interacting, just like the cloud service negotiation, in which you might have more than one agent interacting with the environment? So multi-agent reinforcement learning, of MAL, interact with each other and the environment, aiming to learning policies that collectively optimize a share or individual objectives. So for the agents, you have multiple autonomous agents, each making decision dependently based on the observation and policy, the observed action of other agents. So these are the possibility. You can have interactive agent or you can have opponent agent. And in most cases, the games, especially the games that you are playing online, on most recent game, they're using multi-agent reinforcement learning to they have implemented the multi-agent reinforcement learning. So you have joint and individual objectives. The agent may have shared goals, objective, or individual objective, leading to a spectrum of collaborative and competitive scenario. So observation and action, each agent receive observation from the environment and select action based on the policy. And then for the interaction, agent action influence the state of the environment, and the environment state influence the observation of all the agents. So for the learning paradigm, you can have a cooperative learning paradigm or a competitive or the mix of the two, especially if you have a multi-agent system. And then they can also communicate. In this case, the agent may communicate with each other to share information, coordinate actions, or improve learning. In the case of the exploration, agents face the challenges of balancing exploration and exploitation, considering the action and strategy of the other agent. And you also have the centralized versus decentralized learning. So for the centralized and the decentralized learning, in this case, if you take the case of the Q-learning approach, the fact that the Q-learning is, in the case of the Q-learning, you have the Q table. Each an agent had its own table, but in the multi-agent system, all the agents will be sharing. In the centralized approach, all the agents will be sharing the same table, and they will be updating the same table, and they will be sharing their knowledge. But in the decentralized situation, each agent will be having its own table, and then they won't be sharing any information. So in the joint decentralized policy, joint policy represents a single policy for all agents, and then the centralized policy allow each agent to have his own. A decentralized policy means each agent would have his own policy or his own agenda. So with the multi-agent learning, the interaction of multi-agent can lead to emergent behavior that may be unpredictable based on individual agent policy, which is actually normal, because if they are not sharing their policy, they might be colliding inside the environment or performing the task that was performed by one agent at a certain moment. So for the algorithm, various algorithms address the multi-agent reinforcement learning, including the independent Q learning. So independent Q learning means each agent will be implementing its own Q learning, and then you have the multi-agent deep reinforcement learning. So each agent will be following a DQN, which is deep Q learning approach, and algorithm specific to cooperative or competitive scenario. So cooperative, competitive, in the case of the game, if there's a goal that needs to be achieved, each agent will be competing in order to achieve the goal before the other agent. So you also have the communication strategy that needs to be defined. Explicit communication, agent communicate explicitly through messages. That means one will be sending messages to the other one. And then you have implicit, agent influence each other behavior without explicit communication. In this case, it will be based on maybe the changes on the shared Q tables. In that case, based on the input provided by one agent inside the shared Q table, the other agent will be adjusting their course of action based on that information. So application in various domains, such as robotics, traffic management, game playing, and multi-robot system. These are some of the basic application of multi-agent reinforcement learning. And what are the challenges linked to multi-agent reinforcement learning? You have the non-stationarity. The environment is dynamic due to the action of other learning agent. Scalability, handling a large number of agents can be computationally challenging. So you have also the social dilemma. Agents face social dilemma where individual rationality conflicts with group rationality. Learning from others, agent may learn from policy and behavior of other agents, leading to policy of knowledge transfer. So multi-agent reinforcement learning is a field that explores the dynamic and challenge that arise when multiple learning agents interact. It's finding application in scenario where multiple decision makers influence each other and the overall system behavior. So with this, I think we'll just talk about the implementation if you want to try and run some very simple program about reinforcement learning. I'm just going to make some small comments. So what I'm going to say is very simple. The implementation of reinforcement learning, it's an ongoing process right now. And what I can tell you is this is a little bit of history behind. So when reinforcement learning became a little bit popular, TensorFlow with Keras, where maybe the leading, Google was like the leading company that was maybe like implementing reinforcement learning. So they put in place some facilities inside the TensorFlow framework, and they combine it with the Keras Arrow. And the OpenAI Gym provide the environment for you to design your reinforcement learning environment with Gym, and then use TensorFlow and Keras to create your agent and interact with the environment provided by Gym. But the current issue is that TensorFlow is now moving away from Keras RL, and is kind of difficult to make the current version of TensorFlow interact with Keras reinforcement learning, and is creating a certain discomfort when you are writing programs with it, because you need to identify the correct version of TensorFlow that will be able to interact with Keras, because most example or tutorials that you will be seeing online will be based on Keras and TensorFlow, and sometimes with PyTorch. But it's better to look for the correct version. So in the list I just give you right now, the TensorFlow 2.20.1 is the one of the recent release of TensorFlow that is still compatible with Keras Arrow, that you can use in order to run some reinforcement learning algorithm and see how things are working with it. And then you have the OpenAI Gym that you can use to maybe import and call some environment and use and create your agent with Keras RL, given embed the intelligence coming from TensorFlow, and then make the agent interact with the Gym environment and collect the data you can collect, and see what type of reward or outcome you are producing from that. So for the petting zoo is the framework you can use to design a multi-agent environment compared to a multi-agent system. So it helps you generate many agents at once. And then the last line is about dopamine arrow. Dopamine arrow is basically the Google framework that was designed by Google to replace the Keras arrow. And that dopamine arrow is compatible with the newer version of TensorFlow compared to the Keras arrow, which is not. So with this, I think I'm done with the presentation, and hopefully you try to run some small reinforcement learning programs and see how it works. Thank you. Sorry, any questions?
Any questions, physical participants, online participants? Any questions?
MD, let's give Dr. Kala a round of applause. I think that's a good one.
Okay.
Thank you. I would like to, I would say for want of time, I think that is why we do not have codes for us to actually try. And so I would like to ask where, if there are any repositories, if there are any places where we can go to access these codes, actual codes that have been implemented to solve specific problems in the.
Okay. I think I will share my GitHub repository with you because I implemented a small taxi. They call it what? The taxi environment problem. So basically, you have an agent which is a taxi, and then you provide you implement a small policy to make sure the taxi will be moving around and carrying someone. When it's carrying the person, is receiving a reward. When it's not doing it, there's a small example like that, implementing using simple exploration or random walk approach. And then there's another one using the Q learning approach. And there's a simple example with the deep Q learning. So I think with those three small examples, it should be enough for you to see how reinforcement learning is actually performing in a small program, and enough to inspire you to go further.
All right, he has a follow-up question.
Okay.
The follow-up question is about how available you will be. Maybe somebody has to reach out in case there are subsequent challenges in the application. So your contact.
No problem. I'll share my contact. There's Prof. Adetiba. I think if you want me at any time, you can just call, send anything. I'm available for that.
All right. Thank you, sir.
Okay.
Another question.
Yeah, my submission this time is just sort of like an appreciation for your lecture, Dr. Drews. I really appreciate it, and it kind of relates to my work during my MSc, where I used multi-agent environment to try to solve the problem of service level agreement negotiations. But I want to ask a particular question when it comes to the hierarchical reinforcement learning. You mentioned that the high level, the policies at the high level is very crucial to obtaining an optimal solution. So what are the issues that might affect those policies at the high level that will make the high level not good enough to get to the best solution when it gets to other lower level part of the learning process? What are those things that can affect the high level section of the learning process that can make it to get to a suboptimal solution? I don't know if my question is clear.
So I will try to answer the way I did, what I'm able to understand how it is. So you want to know if the high level policy, how does the high level policy affect the decision making? If I'm not mistaken, is it that?
Yes, that's what I'm trying to ask.
So let us come back to it quickly. So the high level policy is responsible for selecting among different substacks or options. So basically, it's breaking down the problem. You remember the divide to conquer. You cannot just divide because you just want to divide it. There's a methodology in dividing a problem. So you need to make sure every actions that is performed at a certain level, it's like it has a starting point and an end point. You shouldn't define the division process in such a way that the starting point and the end point will be media in the middle of another step. In that case, it will create an issue. So you need to create a division of different substacks in such a way that the substacks you define are clearly independent. If you understand me.
Yes, I do. Thank you very much.
So that is the main issue, being able to do that.
All right, sir.
All right, any other questions? Online participants?
This is Uteme. I just feel indebted to say a very big thank you to you, Doctor, for very amazing presentation, eye-opening. My work is on this line, and I've been reading a number of papers, and in fact, having this session really sheds a lot of light to many things that were dark initially, and I'm sure this will definitely increase the speed. My work is based on cognitive radio systems, using reinforcement learning, deep reinforcement learning, actually, to be able to make more intelligent decisions. And I really want to appreciate your very detailed explanation and some of the concepts that have been mysterious in the past. Thank you so much, and God bless you, sir.
Thank you for listening. Thank you.
All right. Thank you very much. Thank you very much. It's been an insightful session. Would notice we're finishing about an hour, 30 minutes after we were scheduled to, and even the online participants, nobody left. I mean, so it's been very engaging. We've had a great time here in this bootcamp and mini workshop. So once again, thank you very much, Dr. Raymond. Thank you so much for this session that we've just had. So can we just have, I know we've had feedback for his session in particular. Perhaps there are general other feedbacks from participants, online, physical, that want to give at this time. Can we have persons give feedback? Let's take some feedback for this bootcamp and mini workshop generally. Perhaps you want to refer to a previous session, just, general comments. Let's have people. All right. So we have one person here.
Okay, my name is Rachel Kiemi, PhD Computer Science, and I want to appreciate all the facilitators. Thank you very much, sirs. God bless you. And I want to especially appreciate Professor Adetiba's section and Dr. Awelewa. Like, my project is on loss function, that's multitask learning, and I really like to meet Dr. Awelewa to actually understand some of those, vectors. But I'm actually excited because before yesterday, some of those things were looking like film trick. The articles I've been reading. So from yesterday, I now have, but I was able to go back like in the middle of the night. Okay, this is what it is. So this is what P is. Yeah. So this is this. Thank you, Dr. Awelewa. And thank you, Professor Adetiba, for today's session. So like a follow-up. God bless you, sirs.
Thank you very much. All right, we have one more comment here. We would like to have someone online as well give a remark.
Good afternoon, everyone. Okay, my name is Itunu Ajiboye, and I'm a first-year PhD student of bioinformatics. And I want to really appreciate the facilitators of this workshop. And for me, especially, I want to appreciate Professor Adetiba for today's lecture. It was mind-blowing. I actually did a course online on deep learning, but it was looking like, I was not really getting it. But today's lecture actually opened my eyes. I understood. I'm not there yet, but it has set my foot on a path that I know that when I pursue more knowledge on deep learning, I will be able to find my way. Thank you very much, sir, for today's lecture.
All right. So can we have someone online give feedback? An online participant. Edwin Ade. Can you say something? Maybe next time we shouldn't have online participants. They are not saying anything.
I think they have run away, I guess.
Okay. All right. So Dr. Isaac Samuel is saying, great workshop, well done to everybody. Okay. Yeah, okay.
Engineer Delacon, we can't hear you. We can't hear you, but we can see you. We can see what you're writing. Okay, Mr. Akinwale says we are grateful for the sessions. All right. Okay. All right. Thank you very much. Thank you very much. We are seeing your comments, and the facilitators are seeing your comments as well. Thank you so much to everyone. All right. Yeah, thank you. They are also reading your comments. All right. Thank you very much. So, please let's check the WhatsApp platform. We're going to share the post bootcamp survey. Kindly ensure that you fill that survey. From there, you would get your certificates. So ensure that you fill the survey. It also gives feedback, to the organizers, of this bootcamp. So thank you very much. At this point, let's have a word from the principal investigator of the ASPMIR and FedGen Research Group of Capicase, Professor Emmanuel Adetiba. Let's put our hands together for him.
Wow. Awesome. Thanks to everyone. I especially want to let me start by appreciating God. It's been 3 days of intellectual banquet, very, very, very enriching, and I want to really thank God because we didn't have any distraction from beginning to the end. Mm-hmm. Every infrastructure that we needed to use, there was no disruption. There was none of our maybe LOC members running helter-skelter on account of any issue. So we return all glory to God. We also appreciate the Chancellor of Covenant University, our dear Papa, Bishop David Oyedepo, for providing this kind of platform beyond the, we've just had Shiloh. It was an awesome Shiloh for me. Now entering an academic Shiloh, I think we are just drawing from the grace that is upon the life of our Chancellor, and we can't thank him enough. And the management of Covenant University, we got approval for this to happen, and the Vice Chancellor was highly disposed to this happening on the platform of Covenant University. We appreciate the funding agency for this workshop. Google provided funding for this workshop, and I'm sure by the time the report is collated, they'll be really, really impressed with what we have been able to do. And we are actually making a statement that in the 4th Industrial Revolution, Africans are going to have voices, and our voices will count. So we appreciate the funder, the management of Capicase, the team at the Advanced Signal Processing and Machine Intelligence Research. It's a family. We don't just do research. We are also we are well knitted. Okay. And I appreciate Dr. Oshin has been playing a key role on that platform as the coordinator of that cluster. So thank you. And please, let's give her a round of applause because she's been, and all the LOC members, we have Mrs. Ifije, Mrs. Priscilla Ajayi, awesome persons. The success we are recording is because these people were having sleepless nights to ensure that everything runs smoothly. We appreciate Uche is a member of that team, John Wedging, Engineer Bola Kanle, Mrs. Sweet Williams. They are all amazing. We appreciate everyone. I'm sure I've mentioned everybody that, and I want to mention everybody, all the FedGen scholars. I wish I could just mention all your names, but sincerely, I'm super impressed. Your appetite for knowledge, your appetite for depth, this kind of information we are dishing out is not every platform that you will get people getting this absorbed. But I appreciate you, and I want you to give yourself a round of applause. Okay, I can see Dr. Oshin trying to tell me that.
No, I'm here
So please give
because
yourself a round
someone
of
wants
applause.
to comment.
Ah,
So I wanted you to see her.
Mrs. Comfort Lawa, our civil
Exactly.
welfare. I can't forget your name. You are looking so sweet. I can't forget you. Thank you and thank you and thank you. She's the all the stuffs you are, all the chop. That is the brain behind it. So I'm sure she also has plenty things in store for you after this session. So please give her a very big round of applause. It's been awesome. And on the final note, thank you everyone. God bless you. Dr. Welewa, thank you, facilitator. Dr. Raymond Kala, engineer Emmanuel Owolabi, yes, is a personal friend. Dr. Welewa is a personal friend. Dr. Raymond, a personal friend. The keynote speaker, Professor Tako, a personal friend. My host here, we had a good time with his keynote. So everyone is appreciated. And I know we can't wait to have another boot camp because Dr. Kala is not done. I'm not done. Somebody was asking me for the other component of the lecture note. So we can't wait to have a follow-up on this. So on this note, I want to say congratulations to everyone. Please try to maybe enjoy yourself. Let there be a DJ that will play for you to dance and just enjoy yourself after this session. God bless you. Thank you, everyone.
Thank you very much, sir. Thank you very, very much. Let's put our hands together. It's been a very enriching session. All right. Thank you so much. So at this point, let's just rise as we take the closing prayer by Engineer Mrs. Ifije.
Please, let's rise. Father, we want to thank you. Thank you for your faithfulness. Thank you for the very first time we started. Thank you for all of the facilitators, the planning. Thank you so much for Professor Adetiba, for his passion to see that every one of us learn. Father, we appreciate you on his behalf. We thank you for everyone that has participated in this workshop. Lord, we pray specially that this will not just be one of those participations, but Lord, we will go back and feed on everything that we have learned and will become better programmers in the name of Jesus. For all of our facilitators who have brought out of their well of wisdom, we ask that Lord, you increase them on every side in the name of Jesus. As we go, let your presence go with us. We're standing on a very special ground, and this month we have prophesied that we are redeemed to flourish in hard times. Lord, we pray that even as we go, no matter how tough it becomes, we are redeemed. And before the end of this year, you will give us a very special gift to show that indeed we are redeemed in the name of Jesus. Thank you, Lord, because you've answered. Blessed be your name. In Jesus' precious name we have prayed.
Amen.
Thank you so much. Thank you so much. It was great meeting everyone here physically. We thank our online participants once again. All right. Thank you so much, everyone. Meet again in another boot camp. See you.
Okay.